We begin our analysis looking at a standard laboratory rat undergoing a behavioral test. But the mechanism we are studying isn't in the maze, it's occurring at a microscale level inside the animal's frontal cortex. The neuronal membranes in this region are highly enriched in two specific long-chain fatty acids, docosahexaenoic acid, or DHA, N-omega-3, and arachidonic acid, N-omega-6. Both are esterified right at the SN2 position of membrane phospholipids. This schematic map illustrates the distinct enzymatic pathways governing these two lipids. Notice the separate cascades. DHA release is heavily regulated by calcium-independent phospholipase A2, or IPLA2. Arachidonic acid is liberated by separate enzymes, primarily the calcium-dependent cytosolic CPLA2 and secretory SPLA2. Because these release mechanisms operate independently, the healthy brain can selectively regulate structural membrane fluidity and manage downstream neuroinflammatory signals precisely when needed. To test the limits of this regulation, researchers subjected a group of rats to a 15-week absolute dietary deprivation of omega-3 polyunsaturated fatty acids. The immediate physiological result is stark, a 27% drop in total DHA concentrations within the frontal cortex. Facing this severe structural deficit, the brain attempts to compensate. The hypothesis here is that the cellular machinery actively intervenes to slow the metabolic loss and prolong the half-life of whatever DHA remains. This deprivation rewires the brain's enzyme expression to mirror the biomolecular inverse of bipolar pharmacotherapy. Tracing exactly how the brain manages this lipid deficit reveals that dietary fats operate not as passive structural blocks, but as active modulators of psychiatric pathology. Let's focus on the role of IPLA2 at the phospholipid membrane during this state of severe DHA scarcity. The cellular logic is straightforward. To slow the rapid metabolic loss of DHA and keep it embedded in the membrane, the brain must suppress the very enzyme responsible for releasing it. These charts and blots capture IPLA2 suppression in the frontal cortex. Data shows a 21% decrease in IPLA2 activity, aligning with a 27% decrease in protein expression, visible in the diminished bands. Upstream, mRNA levels drop by 50%. The brain does not simply let IPLA2 decay. It initiates an active, multi-tiered transcriptional salvage operation, intentionally downregulating the enzyme to lock the remaining DHA securely inside the neuronal membrane. Now we turn to the enzymes governing the arachidonic acid cascade, CPLA2 and SPLA2. Here we encounter a physiological paradox. While the brain actively suppresses the DHA pathway to conserve resources, the omega-6 arachidonic acid pathway aggressively upregulates. This panel measures CPLA2 and SPLA2 levels, confirming an aggressive enzymatic spike. CPLA2 activity jumps 83%, driven by a massive four-fold increase in mRNA expression. The secretory isoform, SPLA2, exhibits a corresponding 25% activity increase, while its mRNA spikes by 4.6. This concurrent rise is a coordinated response. A known crosstalk mechanism exists between CPLA2 and SPLA2, where the activation of one accelerates the expression of the other, creating a powerful amplification loop for arachidonic acid release. In its desperate attempt to manage the localized loss of DHA, the brain inadvertently spins the arachidonic acid loop out of control, flooding the neural system with N6 lipids and setting the stage for neuroinflammation. These diverging PLA2 cascades dictate downstream production of prostaglandins through functional coupling rules at the synapse. IPLA2 links to cyclooxygenase 1, while CPLA2 links to cyclooxygenase 2. These charts track the diverging fates of these COX enzymes. Mirroring IPLA2 suppression, COX-1 protein decreases 28% via post-transcriptional regulation. In stark contrast, COX-2 mRNA spikes by a factor of 2.4, pushing its protein levels significantly higher. To understand why COX-2 explodes, we look at the transcription factor NF-kappa B. Under healthy conditions, optimal levels of DHA inhibit NF-kappa B activity. When DHA is severely depleted, that inhibition disappears. The unleashed NF-kappa B complex translocates to the nucleus and actively drives the transcription of COX-2 and CPLA2. This structural shift from COX-1 to COX-2 chemically commits the frontal cortex to a highly reactive pro-inflammatory state, characterized by an excess generation of prostaglandins. We can now define the fully realized pathological state of an omega-3 deprived brain, a heavily suppressed IPLA2 cascade operating alongside aggressively elevated levels of CPLA2, SPLA2, and COX2. To contextualize this profile, we look at the standard pharmacological treatments for bipolar disorder, specifically rats given therapeutically equivalent doses of lithium, carbamazepine, or valproate. When we contrast the dietary deprivation data against the cellular effects of these mood stabilizers, an exact opposite pattern emerges. Anti-manic drugs specifically act to decrease CPLA2 transcription and activity. This suppression cascades downstream, lowering COX2 and reducing brain prostaglandin E2. The biochemical profile induced by pure omega-3 deprivation is the exact, verifiable inverse of clinically effective anti-manic therapies. Dietary DHA actively modulates the core neuroinflammatory pathways implicated in bipolar disorder, directly governing the enzymes that control the arachidonic acid cascade. These molecular mechanisms demonstrate that N3-PUFA deprivation is an active trigger for psychiatric susceptibility, shifting the focus from nutritional status to the direct regulation of disease pathways. If you enjoyed this video, please give a like and subscribe. And what would be really helpful would be some suggestions for future videos. Today's video was brought to you by Synestic Systems.